All right. This presentation is getting started with object-oriented programming, which is a bit more than we can fit into 50 minutes, but we'll try to cover the salient points. I know Craig said that the sales job is going to end with their introduction, but I'd like to do a little bit of selling of object-oriented programming to try to convince you why you might want to use it. So at the end of this room, even though, at the end of this presentation, even though there's a lot to take in, kind of like drinking from a fire hose, you might be motivated that there really is power, there really is capability inside this technique. So, why would you want to use object-oriented programming when at first your life will get a lot more difficult? I mean, there's always a learning curve with any new technology because it will get easier eventually. Once you work with it and you become experienced with it, as you practice, your life really will get easier, especially for larger, medium, and large-scale applications. For small-scale applications, it might be a little bit of an overcomplication, but for anything larger, almost than the standard acquire, analyze, present, you'll start to see some return on investment as you learn about object-oriented programming. It's a very intuitive way of looking at things. It's a bit strange at first, but once you start getting into object-oriented programming, you realize that the world kind of thinks in object-oriented terms. I'll try to give examples of that as we go through, but it's really interesting to see correlations between what you're doing in the computer world and what happens in the real world. And I'm not talking about like the Tron movies or anything. Some other movies, reasons. The standard ones that you might give to your manager of why you want to embark on this new thing that's going to take a lot of extra time and effort. Code reuse. With object-oriented programming and most code reuse, it's, at least in my experience, it's not the way you start out, but it's the way you grow. When I first started out, I heard this idea of code reuse. Oh, great, I'm going to create all reuse libraries. I'm going to take all the stuff I'm doing, and I'm going to package them up, I'm going to spend a lot of work polishing them and making them great. And then I never used 3/4 of them ever again. It wasn't until 5-10 years into development I realized sometimes I was using the same code again and again, and half the time it was a huge amount of work to try to extract that code from this project where it was used so I could use it again. It was a bit tightly integrated with things. And then adding that to object-oriented programming, that the light bulb kind of went on. If you package the things you reuse, you'll be able to reuse them easier. So we promise our managers code reuse, but we actually can in some circumstances. Extensibility. I'm not talking about the kind of extensibility that, like a second ago, where you've got a program, you've written it, it does a thing, that's great. Now you've got another project. So you take this code and you copy it and you extend it to make it do the new things. And then you've got another project, so you take that and you copy it and extend it and you've got a new thing. And then you find a bug over there. Well, that bug now exists in 3 separate versions of your program. If you want to fix it, you have to go all 3 places. The kind of extensibility that object-oriented programming gives you when done correctly is changes over here will roll through. So you change it one place and you inherit those things, and later projects, if you've done things correctly, you will inherit those capabilities, those bug fixes, and those new features. There's always the danger in code sharing, but that's another. We'll talk about not in this presentation. Maintainability. This is probably one of the biggest places where I've seen benefit from object-oriented code. Because of some of the features we'll talk about, some of the concepts that you kind of need to embrace, it tends to create separations between different code components, where you'll have things that are doing a very specific purpose, and instead of being in regular programming in LabVIEW, we tend to develop our applications from the start, and they just keep growing. We needed to do a new thing, we add and change some code, and it now does that other thing. Object-oriented programming suggests that you don't do that, you instead create separate modular subsystems. The benefits of that is if you find a bug in one of these subsystems, you more than likely don't have to change any other subsystem. That bug will be localized to this thing, and fixing the implementation here won't affect other things that are related but not via code touching. And that kind of gets into the business of this presentation. That in order to use object-oriented programming and really benefit, the key is to begin to develop abstractions between the different parts of your program. It's a bit of a difficult thing to do up front, but it will definitely benefit. And the cute little graph that I stole from Greg this morning, this is probably going to be a lot of the upward hill, and I want you to leave this thinking that you know everything. Not to let you down later, but that's what the rest of the presentations are, to cushion that flow. So now that we're all convinced, yes, we're going to use object-oriented programming. It absolutely is going to happen. All right, how do you do it? First of all, there's a couple of concepts we need to cover. Some big words that really do mean stuff, but first of all, encapsulation, inheritance, and polymorphism. Those are big enough topics. I've got separate slides on those alone. The first thing I'd like to cover here is the difference between a class and an object, two very specific terms. A class is kind of like a template or a blueprint, or for at least a set of Gerber files. It isn't a thing, but it describes how you will make a thing. An object, we say, is an instance of that class. So if you have a set of Gerber files, you send it out to the board house, you will get back an actual PCB. They probably, I would hope, have a blueprint for the Linwood Convention Center. That blueprint is just some pieces of paper and a shelf somewhere. It's not an actual building. In order to get the building, they have to build the building from the blueprints. Similarly, you have classes that describe how the system will create things, and then when you create them, they will be objects. We call that operation instantiation. Classes and objects have both member functions and member data. Member functions are VIs that are owned by a class, an LV class. Member data are things that are type-def in the class, but there's a specific instance that is owned by each object. Here's where we start to see a little bit of a dichotomy in the LabVIEW world. The native implementation of objects in LabVIEW, LVOOP, is unlike every other kind of object-oriented programming in the world. In every other language, you have a special function inside your class called a constructor. When you want an instance of that class, you want an object from that class, you call the constructor, and it returns to you an object, an instance of that class. LVOOP, you just take the LV class out of your project file and drop it on your block diagram, there you go, it's an instance. It's uninitialized, it has all the default values from your type-def, but it's there. So, in one hand, that's very easy. It's easy to get started. And one of these things up here, the one on the left with request and response, that's a standard LVOOP object. It's just the LV class, and I should say it, in LabVIEW, objects are essentially enhanced clusters. Clusters that can, they have an associated type just like normal, but they also have member functions that can operate, that can access the data inside that cluster. And we'll get into that in a second. For the other type of objects, we call it goop, comes from long ago, like 96.1 days, the Goop Inheritance Toolkit. They created the original IREF implementation in LabVIEW that LabVIEW came out with objects in like 8 or 8.2 or something. So long before NI gave us the capability to do objects, and Devo had the Goop Inheritance Toolkit. And that follows the standard pattern where you have a constructor to get an object. It gives you a reference to that object, and then you have to explicitly deconstruct it to free up the resources. Very important, the lifetimes of different things. With LVOOP, you finish the wire, it doesn't go anywhere, then LabVIEW cleans it up for you. But with Goop, with a constructor, you must also call the destructor, or you just made a memory leak. This kind of thing can also be seen in the far right with the file idle palette. To open a file, you are essentially creating an object. You get a reference to that file. You don't get the whole contents of the file, but you get a reference to that file on disk. So you can read and write, and you pass that wire around. You're not copying the file like you would an LVOOP cluster or the contents of the file in a big string. And then when you're done with the file, you call close file to free up the resources. Oh, now we need the fun parts. Encapsulation. Who here has a wallet? Show them? Yeah. Why do we have wallets? Well, because there's some personal information in here, some information you really don't want other people seeing, some information you need to keep with you, some information that is very specific to you. When we create classes and objects, the first principle of solid design principles is the S, single responsibility. Every class, every object should have a single responsibility, a single thing that it does. It needs to do it and do it well. We do that one of the ways through encapsulation. We take the data that needs to be put together in order to perform a task, and we keep it in one place. It's for everything and everything in its place. The classes own that data and they protect access to it. In LabVIEW, your class member data is by default private. I don't even know if there's a way to make it public. However, you can make it public by creating VIs, member functions, to provide access to it directly, ill-advised, but usually allowing operations on that data to perform an operation. Say if your device driver is an FPGA, you're wrapping up the capability of talking to that FPGA. The FPGA reference never leaves that class. The data, the invoke nodes, the property nodes going to that FPGA never leave that class. Everyone will call a function that will do the work with its internal data. All these member functions in LabVIEW can have a couple different access modes. Public, everyone can read it, write it, and call that VI. Those will be the API that everyone else uses. This is both the most powerful and the most dangerous thing about object-oriented programming. It should provide good encapsulation, good protection of the data of the object. But at some point, your object is worthless if other people can't interact with it. So a proper design will identify the things that people need to access and the things that people should not be allowed to access. Public things are the things that they can access. VIs, member functions that are marked as private in the LV class in the property, the project window. You right-click on each VI or virtual folder and select the access mode from there. The protected things are going to be things that, they're like helper functions that allow you to break up the code that object does into usable or testable chunks, but you don't necessarily want anyone else to do them, or to access them, to be able to call them. Community, let's not touch that, it's a bit advanced. One of the main ways that you will allow other people to access your private member data, because it is private in LabVIEW, is through property nodes. This is dangerous to give people direct access to your member functions. Read access is usually okay, but write access can be very dangerous because you can get multiple things trying to write to the same thing. In computer science, we call that a race condition, and there's no way to determine who is going to write to that variable at what time. One write may stomp over the other write. So protect all of that through member functions, which, because it's a VI that you designed to do a thing, you can protect people from reading things and then writing stale data back into your class. Next, inheritance. This is a little bit of a difficult concept to convey. It's essentially creating a relationship between the various classes that you create in your system. What does this relationship mean? Where the rubber meets the road, the more generic a class, the higher it is in the parentage, the more, use the words, the more generic it is. In this example, right over here is a little thing called a thread. This is a parent class, all of these little guys beneath it. All these guys beneath it. What that means is all of these child classes down there will inherit things that the parent class does. In this specific example, this is a thread parent class and multiple child classes. The parent thread class has things for spinning up an asynchronous VI via dynamically loading it, shutting it down when the system is going away, communicating data between this asynchronous thread running here and whatever other code is running elsewhere. Things that all of these separate threads are going to need to be able to do, that is implemented in the parent class, the more generic class. And then the child class gets more specific. Okay, so this thread class gives us the capability to spin off a thread. Well, which one? Well, the child class actually points to the VI that is going to get spun off. And the parent class allows us to send data to that thread. What should it do with that data? Well, the child class specifies exactly what should be done with each message, with each piece of data. The parent doesn't need to know about it because it just provides the generic, the common functionality. But each thing, each separate thread class has a very specific thing that it needs to do with each piece of data, and it does very different things. One of them is the actual interface to the FPGA. When it receives some data in, it needs to actually write certain of those pieces of data to the FPGA interface. When one of the other guys, a logger, receives that same piece of information, he's going to write it to a file. When one of them is a user interface, you can see way out near the end, there's a nice class there, WebSocket. And, well, this class on the left is, your left, is the real-time part of the application, and the one on the right is the Windows side. They both share a class for the WebSocket, here, right there. And this user interface guy takes actually all the data coming around in the system and forwards it over to Windows. So each of these thread child classes do different things while operating in the same way as defined by the parent, the thread class. Polymorphism, I kind of already touched on this. LabVIEW, long before it had object-oriented programming, it created this concept called a polymorphic VI, where you can have an instance of a VI in your block diagram, and you can choose which of a variety of interfaces you're actually calling. DACMX is one of the most egregious of users of this. It supports digital data and analog data, single channel, multiple channels, single samples, multiple samples. All of that they constructed into one ginormous polymorphic VI, but that's kind of not what we're talking about. What we're talking about in an object-oriented world, the polymorphism, in this diagram you see right in the middle, there's an unbundle for the word thing. That is actually a reference to a thread. Why I didn't make it say thread, I don't know, but it's not and. So in this case, that is a wire of type thread. However, the guts of this is actually a publisher-subscriber system where each of these separate threads can subscribe to specific messages going around in the system. And this is the mechanism that actually goes through for a given message that comes in. It looks up who is subscribed to that message, and that auto-indexes the for loop. And it pulls out of that variant attribute a reference to the individual thread that is subscribed. And the data type of that wire visually doesn't change, but under the hood at runtime, it changes. Because when you get a reference to the class on the left, that's different than the data type for a class on the right, the DAC-V1 or the UI, if you can read it. LabVIEW at runtime determines which of those classes it should call to. Even though the wire is the same generic data type, object-oriented programming, as implemented in LabVIEW, the polymorphism takes the form where any of the child classes, you can have a reference to them on a wire of type of the parent. You can also have the parent type on the wire too. Most of the time that doesn't really do you anything. Most of the time you're going to be treating an interface, and this is where I was talking about, how your public interface to your classes. One of the public interfaces to all of these threads is I want to be able to send data all the time, like hundreds of messages every second. This is done through polymorphism and a mechanism in LabVIEW called dynamic dispatch. It's a fancy word for saying it'll call the right VI at runtime. Before I move on, are there any questions? A lot of glassy eyes. Yes, it's a bit technical, I apologize. That's why we're got more sessions to make it even more technical. Oh, where to start? There is a bit of a divide in the architect realm in LabVIEW about the kind of objects that are right. It's turned into a little bit of a religious debate, it seems. Stephen Loftus-Mercer is the person that both rewrote the LabVIEW runtime compiler, the thing that actually takes your VI code and converts it into machine code. And he's also the guy that wrote the object-oriented support in LabVIEW. Well, he made the compiler supremely optimized for data flow programming. The concept of having data on wires data flowing from one thing, execution occurring in a very structured, ordered mode based on the rules of data flow. And when he created object-oriented programming in LabVIEW, he put them hand in hand. So he made the compiler work even better with LVOOP, or by-value objects. Well, I guess let's talk about this. What does it mean? A by-value reference in LVOOP is essentially the cluster that we saw earlier. It follows the standard LabVIEW semantics of when you branch the wire and you change one of them, that one gets copied and you now have two instances, just like any cluster, just like any piece of data in the system. Using LVOOP, it's more difficult to share data between two loops because one loop changes that data, it changes its copy. The other loop copy is unmodified. That's not a problem by any means. You can create systems that facilitate the copying of data. Queues back and forth, they created the entire actor framework to try to solve this problem. But they're solving a problem that has been solved before. Some of the very first objects were by reference. Stephen Loftus-Mercer really doesn't like these. He says, use them as little as possible and then never again. The problem is every operating system everywhere uses them. Every other programming language uses them everywhere. Most programming languages, this is all you get. And even though they've got downsides, they're very important in very specific circumstances. The by reference is the standard pointer implementation from other languages, C++, C# handles, etc. You construct them, you get one, you construct another, you get another. You don't get another copy just because you branch the wire. Every time you branch the wire to Y reference, you share access to it. So multiple people can access it instead of all getting multiple copies, separate copies. You use this just like any time you would want something like a file or a queue or a control reference. When there's one thing that exists and you need multiple people to be able to access it, when you need to share that data. So how do you know when to use which? I saw this on the YouTubes not too long ago, and it was fantastic. They were actually talking about like ALGOL and other languages that had invented functional programming like back in the 70s. Even though we're just finding out about it now in current technology, yeah, it's been around a long time. We just forgot about it. So, when do you choose when you need to use BIREF? Well, you ask yourself two questions. First of all, is this data private or does it need to be shared? Second, does it need to change or can it remain unchanged? Is it immutable? Only if you need to share it and it needs to change do you need to use, or in my opinion, need to use, is it highly recommended to use some sort of by reference implementation or active framework as that effectively reinvents by reference. Any other time, you can use either one. It might be a bit simpler to implement by val, the standard LVOOP. Finally, this is supposed to end 20 minutes. Oh, I'm going really fast. I highly recommend this toolkit. Long ago before NI built object-oriented programming into LabVIEW, the company called Endevo created the Goop Inheritance Toolkit. They updated it and they maintained it. When LabVIEW came out with object-oriented programming, they updated their toolkit to be able to use LVOOP, but also use their own system. To this day, it still exists. I mean, the company that owned it was bought out like multiple times. Eventually, NI bought it from them, which was fantastic news. The entire CLA crowd cheered when NI bought it, and they announced it at the summit. The only problem is they kind of stopped working on it. Bugs were found. They said, yeah, we'll get to it. Eventually, they let the original author grab a copy of what they had done with it, and he opened it up, completely open source on GitHub. I highly recommend you grab either the NIGDS from VIPM or OpenGDS from GitHub. Either one of them will make your life so much easier. The tools in LabVIEW for doing things with objects are functional, but they don't do a great deal of work for you. These toolkits, from the beginning, automate the creating of classes from various templates. They automate the creation of methods for property access. I mean, they can make property nodes with a couple of mouse clicks and menus. It will investigate your data cluster, the type def that you put into the OE class. List them all. It can create multiple property nodes, read and or write access by selecting multiple things in both of those and hit the one create button, and it just does them all at the same time. It is one of the biggest time savers. It has support for both. It is a screenshot up top, the new LabVIEW native, so it supports operating, creating, and modifying LVOOP classes as well as their own InVivoGoop 4.0 using a data value reference to give you that reference implementation. It has automatic icon editors, class appearance. You can change the appearance of the class wire. All these things you can do in the native LabVIEW environment. They're kind of difficult, at least for me. This toolkit automates the vast majority of the things you need to do in editing and interacting with your objects in the editing environment. I highly recommend it. And that's everything I've got. So, because we've got a couple minutes, so I'll open it up to questions. If you want to ask anything. Anybody still awake? Later.
How often do you find yourself making new classes? I imagine you make them and then you use them for the next 10 years until it doesn't do what you want, and then you might make another one then. Or do you find yourself with a new project, you're just going to make a new class for that, and the next project comes along and there's another class? How often do you do that?
Good question. The question is, how often do I find myself making new classes? All the time. Actually, every new project that comes around has different requirements. I will frequently, go back a couple slides, inside of this project, just in the RT alone, the yellow server on the right to its left WebSocket, the two to the right log, topic, data back, plain data message response, API message request. All of those came from another project. So I didn't have to recreate those. Those are forming a nice reuse library, which I think half of those right now are up on gpackage.io. Anybody familiar with Node.js? Or heard the word? So you know about NPM, the Node Package Manager. Eric Tappan here, I believe, with, sorry? Yes, NGI, thank you. He has created a LabVIEW version of NPM called GPM. It is a free open source toolkit for finding, downloading all manner of toolkits, plugins for LabVIEW. Totally free, open source, fantastic. gpackage.io. Okay. This might break things. Don't tell Craig I'm doing things on his laptop. I know he doesn't use Edge, so I'm not giving away anything private. gpackage.io. There's a command line tool, just like with NPM, that allows you to download and install various packages into a LabVIEW little project folder. You create a little project with the command line tool that tells gpackage what things you have subscribed to. Then with a couple of commands, you can download various packages and it installs the source into that folder, and now you can use them freely in your project. It's fantastic.
Do we know what an I says about like this as opposed to an I package manager yet?
NI acknowledges its existence. They are not, from what I understand, interested in interacting with it in any way. They've got their package manager, just like they have the tools network, which is, I've released things on the tools network. It's not a trivial thing. This is much more like Node.js. It's kind of the Wild West. You sign up, you send Derek an email, you sign up on the form, you say, I'd like to package under this tag, the @CS, and I don't know, he doesn't yet have a browser. Shameless plug. We've got 2 things up there. Okay, so I lied. There's only 2 of them. Craig originally signed up to be the S5 tag. Emailed Derek and he said, oh yeah, sure, you're authorized to submit packages on the @S5 tools, or S5 tag. You don't have to have an @ tag. You can publish your things up there, just create an account with them. And this is a great way of sharing code. If you've ever worked with Node.js, you know how easy it is to import things. Ideally, this would become as prolific, it's kind of the wrong word, but as populated as the Node package manager is, but with LabVIEW code, things that you can reuse, things that, again, you find yourself reusing, so you package in a usable way, not necessarily the things, oh yes, everyone will want this.
If I understand correctly, it's kind of like Node.js or NPM where you have different revisions and versions of packages
Absolutely.
existing with different projects. Unlike the EI package manager where you install a certain version that's kind of moves into your LabVIEW directories, right?
Right, yeah, VIPM moves things into your user lib or VI lib or wherever the publisher says to move it. GPM puts it into your individual project folder underneath the source, not in LabVIEW land. So it's local to that particular project. Is there no question?
Unrelated to that.
Yes.
Back to when would we, can you help define the line between your really simple, like not like object-oriented programming is a little bit overkill, to when is it not overkill? How do you determine that, having not ever used a little detail?
The easy answer is when it makes sense. I don't know. In practice, once you start finding commonalities between multiple operations that can be abstracted, in this example, there's a lot of separate subsystems all running asynchronously. They could all have been in one super VI, but it seemed to make more sense to take each individual subsystem, the thing that talks with the FPGA, make it its own object. The thing that logs high-speed data, make it its own object. The thing that logs statistical information, make it its own object. The thing that talks to Windows over the network, make it its own object. Other systems, I didn't get permission to go into too many details about this. An automated script-based system where the script defines certain activities, certain actions, reading, writing IOs, performing some high-ish level tests or measurements. Each of those are different objects, different classes, inheriting from a step type. And the engine will read through the script, look at the first bit of information, find out, okay, that's a step type. Now go find the object that represents that step type and pass the rest of these parameters to it. And then it, when it's running, it knows how to pick apart those parameters on its own, perform its test, and return its data back to a separate object which manages the results. Does that help? How do you know when?
Maybe go the other way. When would I not use object programming?
I typically don't use OO, or I don't architect it for OO when it's simple, when it's throwaway, when I get into a little bit of difficulty here, because even some of the smaller applications will use objects. It won't be explicitly OO to use inheritance the way it's designed. A program is almost never too small to make use of objects, but it only makes sense to create a large, in-depth application architected with OO once it gets to a large enough where anytime you start finding that this kind of happened, there was a program written in an RT that as it was getting closer and closer to the delivery, more and more features were being added. Each feature would kind of break something else. That's a sign you've gone a little bit too far using the procedural paradigm. There's not sufficient separation between the tasks that need to be performed, the interfaces to your instrumentation, where too many implementation details are getting intermingled. If you can break down a program and look at it as a series of people, actual people around a table doing a process, and you can assign, okay, this person is responsible for managing this. This person is responsible for doing that. That's a good way of looking at an application and seeing if it's a good candidate for factoring or designing as an object-oriented application. Better?
Yeah, so if it is this thing must happen in its entirety, and this thing must happen in its entirety, and that thing, procedural is fine.
Yeah.
But when you start going multiple things at the same time, use probably.
Or I need to interface with a thing, and I don't want to have to know, I don't want this process, even though it's just a straight line. I don't want this overall process to have to know the mucky implementation details of how it's necessary to do that. I mean, you can do the same thing with well-written, say that again, sorry, with procedural programming. VIGs are a nice middle step where you start to encapsulate all of that behavior into a VIG, and you call different modes of the VIG to do those things. I caution that because, once again, that's a VIG everything. It's tending to make a super VI, where it starts to do way more than it really should.
What do you mean by VIG? Sorry.
VI Global, also known as Functional Global, also known as Action Engine.
Thank you.
Okay. Any other questions? Yes?
So do you find yourself basically having program that's architected not only, but you have a whole bunch of hardware abstraction, drivers, layers like that you pull in from OLP. Is that a typical use scenario for you?
Yes, that is 50%-ish of the applications. One of the things we put out, oh no, we didn't, is, never mind. I was going to show, we use a toolkit in S5 rather frequently called the MLA architecture. It's essentially a broadcast architecture, kind of like a low-power, but it's created with just a bunch of loops inside of a VI. It does tend to make a super VI. We'll use object-oriented objects in it. In fact, the MLA architecture is primarily a single object architecture where the MLA object manages all of the messages for you. But then, yes, we will definitely use objects inside each of the loops, which are essentially case structures that handle a specific class of messages that we design up front. So in a way, each loop is kind of like an object, but it's not in any way an LV class or anything in the project. Yes?
You end up mixing and matching one loop, which I guess is just like value, and other objects and classes.
Absolutely. Yes. This application right here. All the green guys on the bottom are by ref. The thread is by ref. Then working this way, request, API message, response, data message, those are all LVOOP. So construct it, fire it, it gets broadcast throughout the system, and then it can leave the wire and get cleaned up for you on its own. Yeah, every application is a mix and match, and I try to follow this.
So your default is only use fire with that's not otherwise.
It is getting more that way as I get lazier and lazier, yeah. I mean, back at the beginning, BiRef was all you got. But, I mean, I shudder to think about trying to use BiRef in this situation where you've got one message coming out and it needs to go to 18 different places. Well, you have to create 18 separate instances of it and clean up 18 separate instances of it yourself, or you get a massive memory leak with hundreds of messages going around in the system all the time. LVOOP does that for you. It's, I love it. So if there's a bug, it's in Matthew, not me. All right. Are we done? 11:30 was? For more questions? Anything else? All right. Well, thank you for coming to Beginning LabVIEW